Hi everyone, welcome to chapter 6, section 1. So in chapter 6, we start off with random variables. So random, not like, oh, that's so random, but like mathematically a random variable is a numerical outcome of a chance process. So a chance process just being like something that we can find the probability of. So like flipping a coin is a chance process, rolling a die is a chance process, or even like being able to pick someone out of a group of people is a chance process. So a numerical outcome just means that whatever I'm doing, the outcomes are all numerical. So like flipping a coin, heads or tails, would not be numerical because heads and tails is not numbers. Okay. So an example of a random variable could be the sum of rolling 2 dice. So like when you roll 2 dice, you get a sum of numbers, and then all the different outcomes could be like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because those are all the numbers that the 2 dice could add up to. And so that's numerical because they are numbers, and then it's all the outcomes. So for the random variable part, we're just saying like x equals. We usually use a capital letter to stand for the random variable. So a lot of times we like to use x, but really you could use any number or any letter. Oh my goodness. So we've talked about this before, but a probability model we're also going to call a probability distribution. So same thing, it's the list of all the different outcomes that you could have along with their probabilities. But now that we are using a probability or a random variable to describe this, I can change my outcomes to have the variable x and then the probabilities, rather than writing it in words like before. We now know we can write it as p of x, so the probability of our random variable x. When we talk about probability distributions, there's some rules that they need to follow. So the rules are, the first one, the x variable should list all outcomes of the sample space, which makes sense. If we're talking about a probability distribution and probability model, we've already said you're supposed to list out all the different outcomes in the sample space. So, got it. Then second rule, all probability should add to 1. Again, obvious, because if you already have all the outcomes in a sample space listed out, remember, everything in a sample space, the probability should add up to 1. So, again, obvious. Last one, probability should be a number between 0 and 1 inclusive. That was like a basic probability rule that we talked about a long time ago. So, yeah, no negative numbers, nothing bigger than 1. Yeah. Okay, so now that we know what random variables are, I want to get a little bit further into detail about the different types of random variables. So there's two. There's the discrete random variable and the continuous random variable. Discrete and continuous is something that we've talked about before, like way at the beginning of the year. So discrete is when it's like a countable number of things. So usually there's a set number of outcomes, so like a countable number of outcomes. Versus continuous is when we're allowed like decimals, fractions, and so there's an infinite number of outcomes that way. So if we were to write out the probability distribution or a probability model, this can be done for a discrete random variable because we can actually list out what all the different outcomes are in the sample space, versus a continuous random variable, continuous because like all the numbers can include every decimal, every fraction in between, then it would be really difficult to list out. So with a continuous random variable, it's harder to write out that probability model. So first I want to focus with the discrete random variable. So let's do an example together. So we're going to pretend in some class of 432 students, let's let the variable x stand for the number of languages spoken by a randomly selected student. So reading this chart, this means that for the students that can speak one language, the probability of selecting a student out of those 432 that can only speak one language would be 63%. The probability of selecting a student who can speak 2 languages is 29.5%, and so on. So the types of things we'll want to be able to do is, like, part A, show that the probability distribution for x is legitimate. So when they say legitimate, it's just asking, is it following the 3 rules that we listed out? So really quickly, we want to make sure that x lists all possible outcomes of the sample space. So basically, our x variable, we have to make sure that there's no one in that group that speaks 0 languages, because that would be pretty sad if they couldn't speak any language, and that there's nobody speaking more than 5 languages. And I feel like from this data that we're given, it's pretty clear. Sure. Okay. Then the second rule was that all probabilities should add up to 1. So we'll double check. So when I add up my 5 probabilities, yeah, I get 1. Cool. And the last thing that we need to check is that all the probabilities are actually numbers between 0 and 1. Well, yeah, looking at all of them, nothing's negative, nothing's greater than 1. Fantastic. So if you're ever just checking or like if it's asking if X is legitimate, we just need to list out like in sentence form, explain, this is fine, we followed the rules. Cool. All right, second thing we want to be able to do is actually find probabilities. So part B says, find the probability of selecting a student who can speak at least 3 languages. Well, at least 3 means 3 or more. So to find that probability, we're just adding up the probabilities for 3 languages, which is 0.065. Add that to 0.008 for 4 languages, and add that to 0.002 for our 5th language, or people who can speak 5 languages. Okay, from that, I think we get 0.075. So that would be our probability of selecting a student randomly who can speak at least 3 languages. All right, so with a probability distribution, because we are describing a variable, we can also talk about the center and the spread, and even the shape for such distributions. So when we talk about the center, we can find the mean of a random variable. This is also called an expected value because basically we're saying a mean is an average, right? So if my random variable was this, the number of languages spoken by a randomly selected student, then if I were to repeat this process many times, like pick a student out of the 432 students, whatever, a bunch of times, then the average amount of languages that that student I pick can speak would be whatever the mean is. So it's like talking about the mean, rather than just using a list of data, we actually have like frequencies associated with the different numerical outcomes that we have. The formula for finding this mean looks like this. So we can write the symbol of the mean as mu with a subscript x, because this tells us this is the mean of the random variable x, or you might see it as e of x, e standing for like expected value. So the formula is the sum of x times p. When I say x times p, this means each of the x values, the random variable, multiplied by its probability. So we're going to do that for each of the outcomes and its probabilities, multiply them together, and then add them all up with the sum. So writing this out, this looks like this. I have the 1 times the probability of 0.63 plus 2 times the probability of 0.295, and so on. When I add all those together, I get 1.457. So the interpretation of this number sounds like this. If we repeated this process many times, this process of randomly selecting a student out of a class of 432 students, many times, the average number of languages that the selected student can speak is 1.457. So everything that's underlined right now, this is basically what you can fill in the blank with depending on the problem itself. But this is going to be your basic interpretation of the mean of a random variable. And again, I want to point out that because this is a mean, this is an average, when we talk about averages, we always want to keep the decimals there, because if you don't, you're basically like rounding too much. When we talk about something on average, we want to know it doesn't have to be an exact number. Obviously, nobody can really speak like 1.5 languages, 1.457 languages, whatever, because that would be weird. How do you speak part of a language? But whenever we talk about averages, always keep the decimals, don't round it. Alright, so if we know how to find a mean, we can also find the standard deviation to talk about the spread of a random variable. So standard deviation, remember, is like how far away each data point is away from the center, the mean. So when we talk about like each data point here, we're looking at our probability distribution, and each of our data points are technically our x variables. So the number of languages that the student could speak. Those would be our data points, and then we're talking about how far are each of those numbers away from our mean of 1.457. So the formula looks like this. There's a big square root over the whole thing, and so on the inside we are taking the sum of x minus the mean. So really like that distance between each of the data points and the mean, we're going to square it in order to get a positive number, and then multiply by the probability corresponding with that data value. And then we're going to do this for each data value, add them all up. Okay, so if I were to write this out so that with the numbers plugged in, then my first data value was 1 minus the mean of 1.457. I would square it and then multiply it by the probability that it corresponded to, which was 0.630. So that was for this column right here. Then I'm going to do the same thing for the 2, the 3, the 4, and the 5. So I've just written it out to the 3 because I got lazy, ... Okay. So obviously this is a lot more effort to type this into the calculator and so on. Let me show you the shortcut way. So with your calculator, your graphing calculator. So in my graphing calculator, I am going to type in my probability distribution into my lists. So remember, to get to the list, it's stat, edit, and then in L1, that's where I'm going to type in all my X values. So the 1, the 2, 3, 4, 5. Okay. And then in L2, this is where I type in all my probabilities. So the 0.630, the 0.295, 0.006, oops, no, 0.65, 0.008, and 0.002. Okay, so I've gotten all my X values, all my probabilities listed out. And so let me go home. So quit second mode to quit. So if you think back to when we first started gathering data and finding the center, the mean, median, all that good stuff, we would go into stat and then go over to the right to highlight calculate 1 var stats. This is still where I'm going to go. Then when I do my list, all my X values were in L1, so that's still the same. The freak list, now we actually have probabilities that we want to use in order to calculate our mean. So here, this is where I'm going to type in L2. So this will tell your calculator X values in L1, probabilities in L2. Go down to calculate, and then it'll calculate everything for you. So this first number is still the mean, which we also calculated by hand. So 1.457, we did it correctly, yay. And then if you look down here, the sigma x, that's the standard deviation. You don't even have to decide between the SX and the sigma x because there's only one. So our standard deviation, if we were to do it out by hand, we would get this 0.67 number, which way faster with a calculator. And so, of course, once we calculate the standard deviation, we also want to be able to interpret this number. So if we repeated this process of whatever, randomly selecting a student out of a class of 432 students many times, the number of languages the selected student can speak will typically differ from the mean by about 0.671. Sometimes you might see the interpretation like describing a typical error instead. Either way works, but of course the context of the problem has to be in the interpretation itself, so that's why we need to have all these underlined parts in there. So the underlined parts, again, fill in the blank for whatever the context of the problem that you're doing is. Okay, so that's all I have to say about discrete random variables. I want to move on to a continuous random variable now. So earlier we said a continuous random variable has like an infinite number of total outcomes in the sample space. The value for x, the random variable, will now take on all values in an interval of numbers. So this means like if I am using the between the numbers like 2 and 5 or whatever, then x, the random variable, can be any number in between 2 and 5. All the decimals, all the fractions, whatever. And so because of that, we can't actually make a chart to show all the probabilities along with the different outcomes because we would be listing outcomes for forever. So instead, we would use a density curve to find probabilities and so on. Specifically, in the statistics class, we would use the normal curve. So we're back to the normal curve calculations. So let's do an example. Weights of 3-year-old females closely follow a normal distribution, so right off the bat they're saying this is a normal curve, with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Let x be the variable, the weight of a randomly selected 3-year-old female. So if we're trying to find the probability that x is greater than or equal to 30, in words this would mean what's the probability of randomly selecting a 3-year-old female who is at least 30 pounds. Okay, so the reason why we wouldn't be able to do this with like a chart when we usually list out our probability distributions is because when we talk about like at least 30, this could be 30.1 pounds, 30.25 pounds, 30.99999 pounds, 68.69421339 pounds, or whatever, like any decimal is allowed. So that's why we would only be able to do this with a density curve. And remember, a normal curve is a density curve. So specifically, they tell us it's a normal curve, so we're going to draw a normal curve. They told us the mean was 30.7. So again, the mean and the standard deviation here is not something that you would be able to calculate because we don't have that probability distribution to be able to calculate it. So they would have to give it to you, standard deviation of 3.6. If we are looking for x being greater than or equal to 30, 30 would be like somewhere over here. I don't know. We'll just pretend it's there. And we want at least 30, so shading to the right. Okay, so from here, this is the same thing as what we've been doing with our normal curves to find probabilities. We are looking for a z-score. So our 30 pounds minus the 30.7, that's the mean, divided by the standard deviation of 3.6 will get me a z-score of negative 0.194. But okay, our z-score table can only do 2 decimal places, whatever. At this point in time, I am also ready to show you the shortcut on finding normal curve probabilities in the calculator. Oof, I've withheld so many secrets up until now. So on the graphing calculator, there is a function for this. So let me turn it on first. If you go into second bars, number 2, normal CDF. So make sure you have normal CDF chosen. Normal PDF is an entirely different thing and we never use it. So normal CDF. If your calculator is updated like mine, it'll ask you for these things. If it just takes you back to the home screen with normal CDF and then a parentheses, these are the numbers that you want to type in this order, separated by commas. So when it asks for lower and upper, it's basically asking, like in our picture, where did we start shading and when did we stop shading? So in this picture, we started shading at x equals 30. So I can type in 30 here. Upper is where I stopped shading, and it technically, remember, a normal curve goes on forever. So I'm going to type in a huge number, like 100,000. Sure. The mean of this problem was 30.7, and the standard deviation was 3.6. Paste. Okay, so when I hit paste, it basically takes all my information and like pastes it into what I was trying to type. So if I scroll over to the left, you'll see it started out as normal CDF, and then this is the part like the not so updated calculators will show. It'll just give you the parentheses, and so you just have to type in the lower, comma, upper, which is like a huge number, comma, your mean, comma, your standard deviation, and the parentheses. Hit enter. This will be the probability or the percentage, if you want to think about it that way. So basically this takes the place of using your table A. So we technically don't have to use that anymore. So even this calculating a z-score part is not as necessary, except because this is a math class. Obviously we're going to show all our work, but then the percentage would just end up being 55.71%. Okay. If you had to calculate a z-score, or like you only have the z-score, you can still do this in the calculator. When we do normal CDF, number 2, instead of the lower being 30, the z-score for a value of 30 was negative 0.194. That was the z-score that we calculated. The upper, because I'm shading all the way to the right in my picture, I'm going to leave it as like 100,000, 1 million, whatever, because it's still going to be a big enough number for me. Except since I'm using z-scores, when we're dealing with standardized scores, the mean is always 0 and the standard deviation is always 1. So now when I hit paste, the probability that it gives me is like slightly different than what I had before, just because of rounding error. Because when I found the z-score of negative 0.194, it was slightly rounded. Okay, but that is the way of finding our probabilities of normal curves without table A. And of course, to complete our problem, we're always going to answer with words. So restating the question, we have the probability that a randomly selected 3-year-old female weighing at least 30 pounds is 0.5771, or if you want to use the 57.71%, both are okay. All right, that's it for this section. Thanks for watching. Bye.